when I was giving this talk, Martin Loebl, who participated in the audience, who was at the audience, he told me about this paper by him and by Stavros Garoufalidis, where he claims there is such a description, such an extension is described. I studied the paper, of course, then, but I have not found whether it is indeed the case. And it seems to me that there is no such extension. Anyway, the paper is interesting for our seminar. That's why I asked Lisa to tell about the results. Значит, я повторю, что в январе этого года в мире, который был давным-давно, и сейчас этот мир даже трудно себе представить, я делал доклад на семинаре в Карловом университете в Праге и рассказывал про весовую систему SL2, то есть весовую систему, отвечающую крашенному многочлену Джонса. И в аудитории был Мартин Лёбль, профессор этого университета, и, собственно, я рассказывал про вопрос о том, можно ли продолжить, доопределить естественным образом весовую систему SL2 для произвольных графов. Поскольку есть теорема моя и Чмутова, которая утверждает, что весовая система, значение весовой системы SL2 на хордовой диаграмме зависит только от графа пересечения этой хордовой диаграммы, но не от других свойств этой диаграммы. Поэтому интересно, можно ли тогда определить весовую систему SL2 на произвольных графах, чтобы она стала инвариантом графов, ну и этот инвариант должен удовлетворять четырехчленным соотношениям. Ну и Мартин Лёбль встал и сказал, что вот у них в статье с Garoufalidisом такой инвариант графов вроде бы предъявлен. Я, естественно, бросился изучать эту статью, но определение инварианта графов там не обнаружил, что не мешает статье быть интересной, поэтому я и попросил Лизу рассказать об этой статье. Так что, Лиза, вам слово, я прошу.
Okay, so I will demonstrate the screen. Is it okay? Do you see my screen? Like there has to be a blank paper.
Yes, yes.
Okay. Well then. So the paper begins by, the paper begins with the following. So, yeah, the name of the talk is the colored Jones weight system. Oops. But I won't be talking, well, very much about the weight system itself, and because the paper addresses some formulas. So, but first of all, we would need the following thing. So we consider chord diagrams on the line. They are sometimes drawn in the circle, but here we draw them like this.
This version is called arc diagrams.
Yeah. So we draw them as arcs over a line, over an oriented line. Yeah, I apologize for the quality of the handwriting. Well, anyway, so on these chord diagrams, we have the arcs. So yeah, we consider the arc diagrams, and for each arc, we can consider a map. So this will be from A of D, where A of D is the set of all arcs of the diagram, to the set of, well, we can consider this just to be some set of, well, of formal letters. Okay. This has to be B0 plus, B0 minus, B1 plus, and B1 minus. And this map will be called the coloring of the arc diagram. So basically we can consider this to be a map to the Cartesian product of the set which consists of a 0 and 1, and the set which consists of a plus and a minus. And we also have to distinguish the arcs that go to I. Yeah, so now...
At the moment, it is not clear. What do we know about these sets? I, B, 0 plus, and so on. Are they finite sets or?
Oh, they're not sets. They are kind of they're.
This is just a letter.
Yeah. I mean, it actually is not, but I think that this is kind of beyond the point of the paper. So we just basically we just want to consider a map which first of all distinguishes some set of the arcs from the other, and we say that they are mapped to I, and then all the rest are mapped to these to this set. So we have 0, 1 multiplied by plus minus.
Вот. То есть мы на каждой дуге диаграммы пишем одну из букв. Вот 5 букв здесь написано. То есть некоторые дуги мы опускаем, это те, которые перешли в букву I. Вот. А на других дугах пишем либо 0 с плюсом или с минусом, либо единичку с плюсом или с минусом.
Yeah, that's precisely what we do. So this map is called coloring on the arc diagram.
Это раскраска дуг диаграмм.
Yeah, we also can note that the arcs of our diagram, they divide the line, the baseline, into the intervals, into closed intervals. So, and all in all, if we have n diagrams, there are 2n plus 1 intervals.
You
so
mean
we call
n
them
arcs? You mean n arcs?
Yeah, so for example, here we have 3 arcs, and so we have everything divided into 1, 2, 3, 4, well, into 7 parts.
Значит, концы дуг делят нашу прямую на 2n плюс 1 участок, если у нас на 2n плюс 1 интервал, если у нас n дуг.
Yeah. So and we begin. So we number them beginning with 0 and get and let's denote them as. So we have S0 and so on. S
2n.
2n. Yeah. Apologize. Yeah. So now we have now we have to associate a certain number to these segments of the line. So what we do is define the number m, which we will define recursively in the following way. So m of S0 equals 0. Then if I is greater or equal to 0, and well, we have to consider two cases. So first of all, let's suppose that our Si, sorry. So yeah, let's suppose that Si here is the ending of Si is just the left end of some of the arcs. Then we can compute MSI plus 1. Yeah, so MSI plus 1 then equals M of Si if so if the corresponding arc, so this arc is mapped to either I or B0, and it doesn't depend what we have, what sign we have. Then we have M.
So the row is the coloring.
Yeah,
Row is the coloring, yeah.
Yeah, so it's one of the 5 letters, and we check if it is one of the 3 written here, then we just have the equality between these numbers M. And if it is not, then we either add plus 1 if we have B1 plus here, and we subtract 1 if we have B minus 1 here as the image of the corresponding chord. So that is, but that is the first part. So there is the second one. We have the case of the. So it might turn out that we have the right end of the chord at the end of the segment Si. Yeah. So if we have this, then once again, everything remains as the number does not change. If we have I or B0 as the image of our chord, and then we have the reverse if we, so yeah, so and then in this case we subtract 1 if the corresponding chord was mapped to B1 plus, and we add 1 if it was mapped to B1 minus.
То есть картинка такая, что у нас есть покрашенная диаграмма. Мы забываем про все те дуги, которые покрашена в цвет I или B0 со знаком плюс или минус. И смотрим только на те дуги, которые покрашены в B1 плюс или B1 минус. И при переходе через конец такой дуги у нас меняется число, приписанное нашему интервалу. Оно увеличивается на единицу, если это конец дуги левый, интервал покрашен, и дуга покрашена цветом B1+, или если это конец дуги правый, интервал покрашен цветом B1-. И наоборот, если уменьшается на единицу, если это левый конец дуги, интервал покрашен, дуга покрашена в B1-, или это правый конец дуги, но дуга покрашена цветом B1+. Well.
Yeah, precisely. So.
And this map M from the segments to where?
Just to integers, yes. So you can basically get, yeah, you start from 0 and then you can either add or subtract 1.
Okay.
Yeah, so now what we also want to define is the weight of each arc. So the weight is the following thing. It depends on these m numbers. So what we have here is this. So if the weight which corresponds to a given coloring and taken on a given arc equals, so this is a polynomial in lambda. So this happens if v is mapped to I, then we have the following. So I'll explain what k and k prime are in a minute. So this happens if we have this, and we also can have another option. So this happens when we have b minus.
In all the cases, we do have linear polynomial in lambda, yeah?
Yeah, we do, because the k's, they are actually the following. So k equals m of s left of v, whereas L is just the segment ending at the left-hand point of V, and the same goes for K prime, but here we have S right. So this is the segment ending at the right-hand point of V.
Значит, теперь у нас есть дуговая диаграмма, она раскрашена, и по раскраске мы написали числа на каждом интервале, на которые концы этой диаграммы делят прямую. Теперь мы еще по этим числам сопоставили каждой дуге вес, который является многочленом от переменной лямбда, линейным многочленом. Но этот линейный многочлен, значит, вот он здесь написан, и он определяется тем, какой вес имеют отрезки прямой, заканчивающиеся в левом, соответственно, в левом и в правом конце нашей дуги. Так, окей.
Yeah, and now we can define this Jones weight system. So it is a map from, so this weight system, yeah, it's a map from the so yeah, this is the vector space of chord diagrams of the rational numbers modular 4-term relation and 1-term relation.
Modular one term also, yeah?
Yeah. Yeah, also.
Okay. Define.
So that makes it, yeah, so that makes it 0 on all the chord diagrams that have no intersections. Which makes sense since we have 0 for
well, define it first of all, and then we'll return to the one-term relation because.
Oh, yeah, okay. So this is mapped to the following field, to the following, yeah, to the following ring. And
Значит, каждой хордовой диаграмме мы сопоставляем многочлен от переменной лямбда.
Yeah, with rational coefficients.
С рациональными коэффициентами, да.
Yeah, so what we have is then that the chord diagram D is mapped to the sum of all the colorings. And then, well, we multiply these weights for all the chords and then sum them for each of the colorings. And that is how the weight system is defined in the paper.
So what we obtain at the moment, we can forget about 4-term and 1-term relations. We can just define such a function on arc diagrams. So we take the product of all the weights of the chords. What we obtain is a polynomial in lambda of degree n, which is the number of the chords, and we sum up over all possible colorings. То есть пока мы можем забыть про всякие четырехчленные, одночленные соотношения, важно, что каждой дуговой диаграмме мы сопоставляем такой многочлен степени n от лямбда, который является суммой произведений по всем хордам, весов всех хорд, а суммируем мы по всем раскраскам наших хорд. Значит, у нас имеется 5 в степени n раскрасок. Для каждой из них мы можем посчитать произведение весов всех хорд и получим многочлен степени n, просуммируем эти многочлены степени n по всем 5 в степени n раскраскам. Окей.
Yeah, so then what they do in the paper is express this function. First of all, well, they construct a matrix. I will explain in a minute what they do, how they construct a matrix corresponding to a arc diagram, and then they then the permanent of this matrix equals this function on arc diagrams, and
The
also
determinant.
no, not the determinant, but the permanent, which is
The
just
permanent.
the
Yeah,
determinant, but you Yeah, so just in case somebody doesn't remember, it's just the determinant, but you do not have minuses, so you put all the signs as pluses in the sum.
Okay, then, first of all, the author states that the resulting expression, the resulting polynomial, satisfies the four-term relations, and hence this is indeed a weight system. It is defined on chord diagrams rather than arc diagrams. On chord diagrams, model of the four-term relations. Yeah.
Yeah.
Mm-hmm. Do they prove this statement at that moment or not?
No, I don't think so. I think they use it right away, and then they know, like, they take it as something known, and then they rewrite it in order to express it differently.
Mm-hmm. Okay,
I think that's their main idea.
Хорошо, значит, авторы утверждают, что так выписанная функция удовлетворяет четырехчленным соотношениям, а потому является функцией на хордовых диаграммах, не только на дуговых, но и на хордовых диаграммах, удовлетворяющей четырехчленным соотношениям, а значит весовой системой. Мы знаем, что пространство хордовых диаграмм по модулю четырехчленных соотношений изоморфно пространству дуговых диаграмм с тем же числом дуг, что и число хорд по модулю четырехчленных соотношений. Well, and it is also easy to see that this function is multiplicative, I believe, yeah?
You mean if we have, like, two parts, so if the arc diagram is split into two parts that do not intersect between themselves, that have chords that do not. Yeah, right, because we just can color them independently.
Mm-hmm.
And then
okay, great. So we may check that the value of this weight system on the chord diagram with a single chord is 0. Yeah? And then it will follow that it satisfies the one-term relation, whatever it is. Значит, эта весовая система просто по определению мультипликативна, потому что мы суммируем по всем раскраскам веса, произведения весов хорд, и если две дуговые, или там дуг, если две дуговые диаграммы не пересекаются между собой, хорды в этих диаграммах не пересекаются, то мы очевидным образом получаем просто произведение двух таких выражений, то есть имеет место мультипликативность. Кроме того, нетрудно посчитать, что значение этой функции на диаграмме, состоящей из единственной хорды, равно нулю, что и называется одночленным соотношением, мы про него можем не думать. Окей.
Yes, so what happens next is that they define the matrix they wish to use. So the matrix is given on an arc diagram if we number the arcs from a left to right. So, for example, if we have something like this, maybe like this. We have them numbered as 1, 2, 3, and 4. And then
this is the order of in which the left ends of the arcs go along the.
Yeah, you just go along the line, and when you meet the arc, you give the number to it. And then, but then we know the following. So if we have, well, we can just consider the intersection matrix first of all. So they denoted IM of D. And so the elements of this matrix are just sine of I minus J if we have an intersection.
So this matrix is skew symmetric. It's not symmetric as we used to. Yeah.
Yeah, it's a bit different.
То есть матрица пересечений, матрица смежности графа пересечений здесь устроена несколько по-другому, чем мы привыкли. Мы ставим на пересечении итой строки изжитого столбца не единицу, если итая изжитая, если итая изжитая дуги пересекаются, либо единицу, либо минус единицу, в зависимости от того, ей меньше же или ей больше же. То есть мы получаем в результате не симметричную матрицу, а кососимметричную матрицу. Симметричную матрицу, в которой стоят нули, единицы и минус единицы. Вот. То есть, другими словами, мы рассматриваем ориентированный граф пересечений, в котором всякое ребро ориентировано всегда от вершины с меньшим номером к вершине с большим номером. Well.
Yeah, they will use this graph later on as well. So the graph will be used as like a middle step in order to prove the formula. So, but first of all, when they have this matrix, they can also do a matrix which is which has the size which is 3 times multiplied by the size of the intersection matrix, which is so the following. Yes, which is
once again it is a square matrix.
Yeah, they just put like 3 by 3 matrix instead of each element of the intersection matrix. Okay. And they do it in the following way. So,
and this square matrix is associated to a colored arc diagram, yeah?
Well, yeah. But well, they define it without like they will just use the colors. They use the colors when they prove the formula, but they don't need them to know them in order to define the matrix, the new matrix.
I see.
Knowing the intersection matrix. So yeah, so they introduced just 4 types of matrices that actually correspond to the colorings we can get, but they can define them without the coloring. So first of all, we have A0, which is, so yeah, this comes from the colorings. 0, 0, 1, 1, minus this. So this is the first one. And we put it instead of an element of the intersection matrix if I equals j. So we put them on the diagonal, but we kind of we expand the matrix, so we have like the blocks, 3 by 3 blocks, and so these are diagonal blocks. Then we have the matrices that correspond to science. So we have this, and we have this. Well, and here we have all these zeros. And we also have, yeah, so those are put into the, into the into the new matrix. These blocks are inserted into the new matrix instead of the elements that were equal to sine I minus j. So if I minus j, if we had I minus j,
то есть -1 is replaced by a minus, and +1 is replaced by a plus. Is it true?
Yeah.
То есть матрица пересечений мы берем, если мы встретили там минус единицу, то мы заменяем ее матрицей А минус. Если встретили плюс единицу, то заменяем матрицей А плюс. Ну,
Yeah,
диагональные нули заменяем матрицей А0, а вне диагональные нули заменяем матрицами B минус и B плюс, которые еще не написаны. Или нет?
No, we have just one of, we either leave them as zeros or we do the following. So if we have this case when we have two arcs, so one is completely contained in another, yeah, so, and they do not intersect, then the zero corresponding to them in the original intersection matrix is replaced by the following. And if it is not the case, then we just leave it as a 3x3 block of zeros.
Okay. Okay. And sorry, is this for the upper element below diagonal or above diagonal? Or what? This is.
Oh, it's when I is like, yeah, sorry, I forgot to write. So I should be contained in J. So this is just what, so we have this, I am, well, the original intersection matrix, so we had something, some zero in the place ij, yeah? And so if this is the case, if the chord number I is contained in the chord number J, so this must be the ones that come below the diagonal, I think.
Yeah. Хорошо, значит, у нас бывает, если поддиагональный нуль заменяется матрицей АС, если он соответствует вот нарисованной ситуации, когда дуга с меньшим номером содержит внутри себя дугу с большим номером.
Yeah, we just
сильно несимметричную матрицу размером 3n на 3n.
Yes, that's what happens. And then, well, the theorem that is stated and proven in the paper says that if we have this, so the elements of the matrices, the sum of the elements of the matrices, they are polynomials in lambda, right? So when we take this expression, when we take the permanent of the matrix, of the new matrix, this IMJ, which is the one that has 3x3 blocks, then the theorem, they state is that the weight system equals the permanent of this matrix on each chord diagram.
Лиза уже напоминала, что перманент матрицы это определяется так же, как ее определитель, только в определителе мы некоторые произведения элементов матрицы берем со знаком плюс, а некоторые со знаком минус. А в случае перманента мы все эти произведения берем со знаком плюс. Вот. Поэтому перманенты, в каком-то смысле изучать гораздо сложнее. И они устроены более сложно, чем определители, и реже имеют геометрический смысл.
Sorry, and the WJ is this 3n by 3n matrix?
No, the WJ is just the weight system. So this is the map which...
I see, okay.
Yeah, I can return to... Okay, yeah.
То есть вот этот многочлен степени n равен, который мы сопоставили каждой дуговой диаграмме, он равен перманенту вот этой вот выписанной нами матрицы.
3n на 3n.
3n на 3n матрица, да. Well, great.
Yes. So now I will. Well, so to prove this, they do a lot of like rewriting. But the thing they use as like a huge step in the proof is that they use the labeled intersection graph of this chord diagram. So they use a lot of constructions in this paper, but still, so they call it Lij of D, and yeah, so what they do first is this. They well, for example, if we have this chord which was drawn before, just a second. Yeah, this one. So here we can see that, for example, chord 1 intersects all the other chords, so does chord 4, but chord 2 and 3 do not intersect. So what we have here is that we draw just the graph which, well, reflects these intersections. We have 1 which is connected to all the rest, all the other vertices, and we have 3 and 2. But then they do not simply leave it as it is, but they orient each edge from the smaller vertex to the larger one. And then they also want to keep this data to know when one chord is contained in the other. So to do this, they draw, yes.
So sorry, what is Lij of D again?
So this is the graph I'm building right now. So first of all, we just draw the intersection graph.
Intersection graph. Labeled intersection graph. LIG.
Yeah. It's labeled intersection graph. So yeah, and I'm explaining the construction right now. So yeah, first of all, we just draw the unoriented intersection graph, and then we order the edges from the smaller vertex to the larger one, and then we also put something they call red edges that correspond to the pair of chords with numbers ij, such that I is completely contained in j. So those ones always go from the vertex with the larger number to a vertex with a smaller number, because I is always greater than j if we have it contained in j.
Окей. Значит, мы по хордовой диаграмме, по дуговой диаграмме строим такой помеченный граф пересечений.
Yeah, but that's not all. We also add loops here. Oriented counterclockwise, I think.
This doesn't matter.
Yeah. Oh. Yeah, since they get, well, they kind of only want to know the number of the loops later on, I guess, yes.
So am I correct that this labeled intersection graph is, we add some edges to just ordinary intersection graph?
Yes.
Like to those indices, to those arcs which do not intersect, and somehow lie one into another.
Inside, yeah.
Inside, yeah.
Yeah. That is because, well, they just want to keep track of this stuff we did with the matrix here.
Мгм. Значит, в этот помеченный граф пересечений, значит, мы делаем его ориентируемым, ориентируя каждое ребро от вершины с меньшим номером к вершине с большим номером. В каждой вершине мы добавляем петлю, и еще мы добавляем другого цвета. Как назвать этот цвет? Скажут?
You know, they're supposed to be red, but I could not find red here. So, yeah.
Будем считать, что это красный, да. Если вершина с большим номером, дуга с большим номером содержится внутри дуги с меньшим номером, то мы добавляем ориентированное ребро красного, нового красного цвета из вершины, из соответствующей вершины с большим номером в вершину с меньшим номером.
Yeah, but then, well, yeah, what they do then is they consider this. Yeah, so they consider first of all to each of yeah, so they call the edges arcs here when they are oriented. But anyway, to each of them we can associate the variable, the formal variable xe. And then what they do is consider this. Yeah, so when we have, I don't know, for example, so E equals UV, where UV are the vertices, and if we start at U and go to V, so this reflects the order of the vertices, the orientation of the edge. Yeah, and then what we also do is that on this, so this could be called a digraph, which is just a graph with oriented edges, and so, well, yeah, the graph with oriented edges, which for which we can consider the set of its arcs and the set of its vertices. And then they what they do, so yeah, so the when they do this, so this helps them in the proof. So the outline of the proof goes like this. They want to define an acceptable object on the digraph. This acceptable object is something. It's a collection of arcs K plus something called a thickening. So this happens at one end of each arc.
Значит, теперь arc, дуга, означает уже ориентированное ребро в графе, а не дугу, которую мы...
Yeah.
Я правильно говорю, да?
Yeah. I can call them edges if that is more convenient.
Да, лучше так.
Okay.
Можно arrows?
Okay, I'll let them be arrows indeed. Oops, nope. Also, okay. Arrows. Yeah. So here we have at each arrow. Yeah. So this collection plus the thickening. So the thickening is just we basically a way to mark one of the ends of each arrow. So it's called acceptable if we have the following conditions satisfied. First of all, if the arc, so let me denote arrows by this. This just means that it starts at I and ends at J. That are the numbers of the vertices that correspond to the chords, to the arcs in the diagram, in the original diagram. So if it is red, then both IJ and JI may belong to K.
But not both?
No, both.
Mhm.
Both. But they must be always thickened at I.
Mhm.
Thickened at I. But if it is not colored, if it is not, so we have red and uncolored arrows. So then, well, then those cannot appear together. So in this case, they cannot both belong to K, but thickened, they can be thickened at both I and J. In the sense that they cannot be simultaneously thickened at two ends of the arrow, but we can choose either the end which is adjacent to I or to J.
Значит, вводится новое понятие утолщения, thickening. И если стрелка красная, то есть ее нет в исходном графе пересечения, мы ее добавили, то концы этой стрелки можно утолщать оба конца или
Yeah, so
нет.
if the arrow
Нет,
is
утолщать у нее мы можем
yeah.
только левый конец, только начало стрелки. Да? Если стрелка не крашеная, то есть лежит в исходном графе пересечения, то утолщать мы можем в любом из ее концов, либо в начале, либо в конце.
Yeah. Yeah. So then that is not all. There are also conditions that each vertex of V has either 0 or 2 or 4 adjacent thickened arcs.
Arrows.
Yeah, sorry. Arrows. If we have a loop, then well, yeah, we just choose. So we always consider the loop to be thickened at the beginning.
Mm-hmm. Okay.
And then we also have the following condition that exactly half of the arcs of the arrows, sorry. arrows adjacent to a vertex are thickened at it. Yeah, and besides, also if we have this if two arcs are thickened at a vertex,
2 arrows.
yeah, if two arrows are thickened at the same vertex, then one arrow comes to the vertex if we consider its orientation, and the other leaves always. So if we have this object that satisfies the mentioned conditions, then we call it acceptable. And what they do now is they write the following function of the graph. The sum of all acceptable objects. The following expression. Yeah, this was supposed to be the multiplication dots.
Okay.
Yeah, so here, what all this means. So first of all, xk is just the product of all the formal variables that correspond to the arrows that belong to k. It's just this. So e, k, x, e. And then the degree 4 of k is just the number of the vertices incident with 4 arrows of k. And a of k is the number of arrows of k with the initial segment thickened.
That's the definition. Yeah?
Yeah, that's the definition. So they call this G a partition function.
Mm-hmm.
And what they do first, so they have the proof split into 2 parts.
Let me come. На русский язык partition function переводится как стат-сумма, статистическая сумма. То есть мы берем какие-то состояния в нашем графе, в ориентированном, в помеченном графе, мы берем состояния, которые называем допустимыми, и вот суммируем что-то, в данном случае 2 в степени Дек-4 это количество вершин степени 4, что ли, да?
Да.
Количество вершин степени 4 на лямбда плюс 2 в степени дополнительной степени и на произведение всех пометок ребер, входящих вот в это допустимое состояние К. Значит, К – это некоторый набор ребер, который является допустимым при выполнении условий, перечисленных на предыдущем слайде. Вот. И мы получаем некоторый многочлен от лямбда, ну и от переменных, соответствующих ребрам. Поэтому он не может быть непосредственно многочленом, совпадающим с весовой системой, с интересующей нас весовой системой. Окей.
Yes, so the huge part of the proof, basically what they do is that first of all they announce the following. Yes, so this will be more like an outline of the proof because I think it's very long
Yeah, of
and
course.
yeah,
Of course. You're right.
I mean, yeah, and I unfortunately also do not have a convenient tablet right now, so I apologize once again for the handwriting and all of this. But anyway, so what they announce is that the weight system, the value of the weight system on an arc diagram equals so this J, the partition function, taken on this graph, but also since we do not have any XEs in
Should it be LIJ?
oh yeah,
LIJ for ID.
yeah, it's just this. It's the graph, the original graph. Yeah, I apologize. So this is the oriented graph with loops and red edges and all of this. And we take just all the acceptable objects of this graph and well, compute the partition function, and then they claim that if all of the formal variables are taken, if it's evaluated at a point where all the formal variables are equal to 1, then we get the function which is exactly the one to which D is mapped via the weight system.
So this J capital is the partition function from the previous slide.
Yeah.
Mm-hmm.
It's named the same.
What I do not understand is what is the reason to introduce this xk, because we are, anyway we are going to set them equal to 1. Значит, если в предыдущем выражении для статсуммы положить значение переменных, отвечающих всем ребрам, равными единице, то получается в точности весовая система, которую мы определили сначала, но это промежуточное определение, видимо, необходимо для доказательства того, что так определенный многочлен удовлетворяет четырехчленному соотношению. Да?
Я просто думаю, что там эти переменные, когда считается статсумма, они же входят экспоненциально как-то там складываются, и поэтому важно сначала посчитать статсумму, а потом положить их равными единице, а не наоборот.
Может быть. Okay, Lisa.
Yeah.
Whether the authors introduce a four-term relation for this labeled graphs or not?
Could you please repeat what the question?
Они вводят четырехчленное соотношение для этих помеченных графов или нет?
В смысле?
Ну, вот,
you mean do they draw like a picture of the relation?
No, for ordinary intersection graphs, we have a four-term relation for ordinary graphs, which is such that the mapping taking a chord diagram to its intersection graph takes a four-term relation to a four-term relation. Is the same true for label graphs? Do they have four-term relation for graphs? Okay.
I do not think they do it explicitly, at least.
Okay.
I mean, they do have, at some point in the proof, they do have like some statements that say that, well, what we get does not depend on something we choose, like in the graph.
Great.
But I mean, at least it's not mentioned. Like they do not call anything the four-term relation.
Okay.
Yeah. So what I could probably do now is just give the idea of what they so they split everything into two parts. First of all, they prove this formula displayed here, and then they prove that the right hand side equals the permanent of the matrix.
Mm-hmm. Yeah, I see. Do you have examples of computations of the weight system they define?
Nope, not completely.
No. Mm-hmm.
But I probably could do an example, like if we don't have too many chords, we could just check it, I think.
Can for example, for two chords, for two intersecting chords, just we would be able to have a look how
Yeah.
the system could be computed.
Yeah, okay, so let's just do this. Okay, so we have two intersecting chords. First of all, what we know now is this, we want to compute, well, let's just use the definition first, right? So if we use the definition, which is, yeah, just a second. So we have the segments here, we have 5 of them, right? M of, so we have S0, oh my, S1, S2, S3, and S4.
I'm afraid writing out all the 5 times 5, 25 colorings would be awful. Maybe the matrix definition is easier to handle. Don't you think so?
Oh yeah, but what are we trying to check then? Like what?
Not we are not going to try to check, but just to see the result. What will be the which polynomial we obtain as a result of the computation?
I see. Okay, yeah.
We obtain some polynomial in lambda, and it will be interesting just to.
Yeah. Okay. Just a second.
Mm-hmm.
So we will use the graph instead. So, the graph, first of all, what we have here, first of all, is that, well, we have two vertices, right?
Yeah.
I and J.
1 and 2.
Yeah, right. Sure. So we have 1 and 2, which means that the matrix is 4 by 4, the original adjacency matrix.
It's 2 by 2. Why 4 by 4?
Oh, yeah, 2 by 2. Yeah, I meant it had 4 elements. I apologize.
It has 4 elements.
Yeah, so, and since those intersect, and we have, so this is 1, this is 2. 1 intersects 2, but 1 minus 2, so here we have minus 1. Here we have 1.
Mm-hmm.
So it gets replaced by the following. So we have 0, 0, 0. This 1.
So we replace each of the diagonal zeros by this 3 times 3 matrix.
Yeah. So it is just repeated here.
Mm-hmm.
Yeah, and then now we have to replace this by a minus, which equals, so yeah, we have -1, and all the rest is zeros. And here we have 1,
Там, по-моему,
1.
слишком много нулей. Там 6 на 6 матрица.
Yeah.
Но у вас как будто 7 в первой строчке чисел.
Да, слишком большая матрица получилась. У вас последняя колонка раздвоилась.
Yeah, it did. I apologize. Yes, this should be yeah. Just a second. So this has to be 0, 0, 0. Yes, okay, since we have many zeros in the first column, let's just yeah, so we write it as this. Okay. So then we probably want to use like the
Okay, what we see is in fact that the resulting polynomial will not be of degree 6 because we see 2 columns which do not contain lambdas, only constants. I'll try to compute the permanent by the computer program. So you may don't try to do that right now.
Wait, but won't we have just we have to have the polynomial of degree 2, do we not?
Probably we would like to, but we will see whether this will be indeed the case. It's not. As far as I remember, there are some computations in the paper, yeah?
They compute the said matrix for the case of 4 chords, the one I drew before. But they do not compute the permanent explicitly. They just, well, they write the matrix like this down. And they also, well, yeah, and they also provide, at the end, they provide a program you could use. Like, yeah, so they say that they have they said that actually that they have the website where they have this Jones permanent package, they call it. So yeah, they kind of advertise it. They say that if you download it from their website, then you can use it for computations. They give some code in Mathematica 4.1, they say.
I see. Up to now, I have not yet entered the matrix.
I could probably try to compute it like maybe I could try to compute it, you know, on a paper and then write out the result, because I don't think it's that bad, because I mean, it's 5 by 5, so maybe it's just, I don't know, or if it is more convenient, I could actually try to write it on the board right away.
Okay, let me do that. Just wait a couple of minutes.
Okay.
Um, okay. The next one. Ooh. Okay, and now lambda minus lambda. Okay, the answer is lambda times lambda plus 2.
I obtained -6 times 2 plus 6.
-6 plus 2.
No. The same, but with other sign.
Yeah, but correct. Negative lambda times lambda plus 2.
Oh, great.
Well, at least it's of degree 2.
Yeah, it is of degree 2, so this works reasonably. This works reasonably. Reasonably well. By the way, we know from the initial construction that the matrix is a block matrix. It consists of 3 times 3 blocks. Does this help to compute the permanent or not? Don't you know?
Sorry? The blocks? Like...
Мы знаем, что матрица состоит из блоков 3 на 3. Мы не можем заменить там каждый блок его перманентом или чем-нибудь, чтобы... Вряд ли, да?
No, I don't think so. Yeah, but they actually do, by the way. Yeah, I apologize. So they actually do compute this for the case of, well, for the one I drew before, which was 4 chords. Yeah. So they have 1, they have 2, then they have 3 like this, and 4 which intersects all the rest. So yeah, so we have 1, 2, 3, and 4. And so they claim that for this one, they have, well, degree 4, and they have 4 lambda to the power 4 plus 16. Oh, oops. And minus 40 lambda. Yeah, so they claim that this is what happens for this one, but they do not like give any insight except for the code.
Okay, thanks. I think we must stop here and let me comment. Let me comment on the results. So first of all, I do not know what is the relationship between this polynomial and the one I usually refer to as the SL2 weight system. То есть, во-первых, я не знаю, какое соотношение между многочленом, которые считают Loebl и Garoufalidis, и тем многочленом, и той весовой системой SL2, с которой мы работаем. For example, the leading term of the polynomial here is 4 times lambda to the power 4, while we always have 1 instead. The leading coefficient is always 1 in our considerations. The other, however, it could happen that there is an easy variable change that leads to that transfers one polynomial into the other one.
By the way, all coefficients are divisible by 4.
Yeah, all the coefficients are divisible by 4, but for the SL2 polynomial, we know that the signs of the coefficients alternate, and this is not the case for this polynomial, and so on and so forth. То есть, возможно, этот многочлен какой-то простой заменой переменных переписывается в наш многочлен вот, соответствующей весовой системе SL2, но я эту простую замену переменных не знаю, может быть, кто ее напишет, будет уже полезно. Another point is that let me return to what I started with this seminar with. Martin Loebl suggested that this polynomial, the polynomial they define is well defined for arbitrary graph. And this is true, but the graph is not an abstract graph. Instead, it is a very specific labeled graph. And if you have an abstract graph, an ordinary simple graph, which is does not contain any orientations, any additional arrows that are not do not correspond to intersection of arcs, and so on. We do not know how to write out this polynomial as well. То есть Loebl отвечал на мой вопрос, как доопределить, как распространить весовую систему SL2 для произвольного графа. И вот именно такое определение он, судя по всему, имел в виду. Но это определение годится не для абстрактного графа, простого графа, с которыми мы привыкли работать, а для графа, помеченного очень специальными пометками очень специального вида. Нужно, чтобы он был ориентирован, и в нем есть еще какие-то ребра дополнительного красного цвета, которые не попадают в исходный граф пересечений. В общем, не видно причин, по которым этот многочлен можно определить для произвольного простого графа без пометок и ориентации. Поэтому я не нашел в этой статье ответа на тот вопрос, который я задавал с самого начала. Okay, thanks, Lisa. The presentation was clear. If anybody has questions, comments. Okay, then see everybody. Hope everybody is well, and see everybody in a week.